What if your stormwater management system could accomplish more than just preventing floods? Imagine if it could actively improve the local ecology, reduce long-term maintenance costs, and become a key feature for a project's marketability. Most engineers view stormwater design as a regulatory obstacle that requires management and minimization. Is that the complete engineering picture? This limited view is costing firms a critical opportunity for innovation. This video will explore the core principles of modern stormwater design that leading firms use to turn compliance obligations into strategic advantages. We will demonstrate how a refined engineering approach creates lasting value that extends far beyond initial construction. The central challenge in modern stormwater design extends beyond simple water conveyance. It is rooted in managing immense liability. Consider a standard commercial development project. An engineering firm proceeds with a design based on conventional hydraulic calculations derived from historical rainfall data. The objective is the efficient removal of stormwater from the site through a traditional network of pipes. This familiar methodology treats stormwater as a waste product to be disposed of quickly, a perspective that introduces significant, often unacknowledged risk from the project's initial stages. The resulting design successfully meets all minimum regulatory standards outlined in the municipal code. However, this compliance is deceptive, as the design's assumptions create a practically fragile system. It fails to adequately account for two critical factors: the increasing frequency of extreme weather events and the cumulative hydrologic impact of regional development. Upstream urbanization consistently increases impervious surfaces, altering runoff patterns in ways that historical data cannot predict. This creates a latent vulnerability, as the system is engineered for a theoretical storm event that no longer represents real-world conditions. The materialization of this vulnerability occurs when a severe storm impacts the region. The runoff volume and rate quickly overwhelm the system's design capacity. Undersized pipelines surcharge, causing manholes to overflow and resulting in widespread flash flooding across the new development. The destructive high-velocity discharge scours downstream channels, causing severe bank erosion and habitat degradation. Simultaneously, the first flush of runoff, laden with pollutants like hydrocarbons and sediment from the new construction, bypasses the overwhelmed system and flows directly into a protected watershed, triggering an immediate environmental non-compliance event. For the client, the consequences are severe. They face costly repairs for inundated property and infrastructure, alongside significant reputational damage. More critically, they are issued substantial non-compliance penalties from environmental agencies for the illicit discharge. The engineering firm that certified the design is now exposed to profound professional liability. Legal action from the client becomes a distinct possibility, coupled with a costly mandate to redesign and retrofit the entire system under far more stringent regulatory scrutiny. This represents a catastrophic failure of risk management. This cascading failure starkly illustrates the disconnect between meeting baseline codes and delivering a resilient, legally defensible design. A system can be compliant on paper, yet remain fundamentally inadequate over its service life. The reliance on static, historical data in a dynamically changing climate and built environment proves to be a high-risk proposition. The design failed not because of a calculation error, but because its core philosophy was misaligned with the actual environmental and hydraulic stresses it would inevitably face. Upon analysis, the most financially damaging aspects of the failure stem directly from three specific areas of technical oversight. First, an inaccurate hydrologic analysis that fundamentally underestimated the total runoff volume and peak flow rates from the contributing watershed. Second, the subsequent specification of undersized hydraulic infrastructure, including pipes, inlets, and culverts, lacked the capacity to manage the actual storm flows. Third, a complete lack of integrated velocity and erosion controls designed to safely dissipate the energy of the concentrated flow before it could cause destructive erosion downstream. These are the specific failures that lead to project overruns and severe regulatory penalties. Such reactive problem-solving represents an obsolete and high-risk model of engineering practice. It is a posture that waits for failure to occur before responding. The industry now demands a proactive and integrated approach to design, shifting the focus from mere compliance to comprehensive risk mitigation. This fundamental shift is essential to address these known points of failure from the outset, ensuring long-term hydraulic performance and protecting all project stakeholders from predictable and entirely preventable liabilities of this nature. A design team can transform a stormwater system from a costly obligation into a value-generating asset by fundamentally rethinking the traditional approach. Rather than treating stormwater as waste to be removed, an integrated water management model treats it as a resource. This strategy leverages advanced modeling capabilities to develop systems resilient to modern environmental pressures and harmonized with the project site itself. The objective becomes maximizing functional, ecological, and economic benefits to strengthen a project's long-term viability. At AXA Engineers, the process starts by creating a dynamic digital twin of the project site and surrounding watershed. Unlike static calculations based only on historical rainfall data, the digital twin is a comprehensive data-rich model simulating real hydrologic and hydraulic interactions. It accounts for topography, soils, land use, and existing infrastructure, providing a realistic baseline for evaluating design options. This foundational step is essential to understanding how water moves through the site and anticipating system behavior under a range of conditions. The model is not a one-time analysis, but a living tool throughout design development. A dual-team working model enables continuous simulation and collaboration across time zones. By operating in overlapping shifts, teams remain aligned with clients' working hours, accelerating design iterations and supporting tight deadlines. Robust data security and anti-leakage protocols are implemented to comply with international legal standards, ensuring protection of client intellectual property. This agile framework allows adjustments and refinements to proceed efficiently without delaying the project. Within this environment, numerous hydrologic scenarios can be simulated, from frequent minor storms to rare, high-intensity events, reflecting the upper range of climate projections. These simulations are used to test the performance of modern stormwater control measures, SCMs, including permeable pavements, infiltration trenches, bioretention basins, and green roofs. Each SCM's effectiveness is quantified under varying stress conditions. Evaluating the integrated system as a whole allows potential weaknesses to be identified before construction begins. This iterative process makes it possible to optimize SCM placement, sizing, and configuration with precision. Simulation results guide decisions such as locating bioretention basins to intercept runoff or specifying aggregate depth beneath permeable pavements to balance infiltration and structural needs. The goal is to exceed regulatory requirements for water quality treatment and quantity control, satisfying mandates like the Clean Water Act. Designs are fine-tuned to meet measurable targets for pollutant removal and peak flow reduction. A central challenge lies in balancing engineering performance, long-term maintenance, and ecological benefit. For example, an effective bioretention system must also feature vegetation adapted to the local climate and capable of thriving with minimal care. Achieving this balance requires specialized expertise and sophisticated analytical tools to manage complexity and deliver solutions that are sustainable over decades. Proactive modeling significantly reduces project risk. Instead of relying solely on theoretical calculations, a performance-based report backed by extensive simulation data can be submitted to regulatory agencies. This transparent, evidence-driven approach builds confidence among stakeholders, minimizes requests for additional information, and lowers the likelihood of costly redesigns and penalties for non-compliance. To enable this process, AXA Engineers utilizes a suite of licensed software tools. Detailed site modeling and terrain analysis are performed with Autodesk Civil 3D. Hydrologic and hydraulic behavior is simulated with the EPA's Stormwater Management Model, SWMM, and the U.S. Army Corps of Engineers HEC RAS. Proprietary scripts further support optimization, allowing teams to evaluate many alternatives quickly and identify the most effective solutions. This technology stack ensures each system is designed for compliance and cost-effectiveness throughout its life cycle. The result is a stormwater system that becomes an asset rather than a liability. It can provide green space, improve local ecology by reducing pollutants and recharging groundwater, and deliver a clear return on investment through improved safety, elimination of retrofits, and reduced long-term maintenance costs. The evolution of stormwater engineering demonstrates that the most effective designs are those that treat water as a resource, not a waste product. This paradigm shift from mere compliance to holistic integrated management is where leading firms create lasting value and decisively mitigate long-term risk. Partnering with a dedicated outsourcing specialist such as AXA Engineers brings over 15 years of targeted expertise into your project team. This collaboration has the power to transform regulatory requirements into opportunities for sustainable innovation, cost efficiency, and enhanced project appeal.